Okay. Sorry. Subscripts don't work so well. Okay, so this is playing off of something that you guys have done in class. It says, which of the following compounds form hydrogen bonds between its molecules? The first one, does it? Yes. The second one, does it? Because you just have the fluorine, right? So there's nothing trailing that fluorine that is a hydrogen. So, okay. What about the third one? That's right. So only the first one would be able to. Which of these compounds will form hydrogen bonds with a solvent such as ethane? In other words, which one is going to be able to be dissolved in ethane? I'm sorry, ethanol, sorry, not ethane. One, okay. With the others? Shaking your head. So would it be partially soluble? It would be soluble. It would be soluble, yes. Yep. Okay, so what does ethanol look like? What is the chemical formula for ethanol? What was that? Yes, they all would. Okay, but what does ethanol look like? So it's an ethyl group, so it's CH, H5, OH. Okay, this guy's always going to form a hydrogen bond. So you're going to have hydrogen bonds forming here, right? You're going to have hydrogen bonds forming here, and you're going to have hydrogen bonds forming here. So in all three cases, it's going to be dissolvable, right? So if you think about it, this guy is, let me erase. Okay, so this guy here, what does the structure look like? What type of compound is this? You guys remember? Okay, it's an ether. So then, okay, so can this oxygen form a hydrogen bond with this hydrogen? It can, right? So then it would, right? Which would make it dissolvable. Plus you have that hydrocarbon, right? Okay. What about this guy? We have a fluorine at the end, so then we have this one, 2, 3. Would it be able to form hydrogen bonds? Yeah. Okay. That's right, which is all written right here, the answer, right? It's okay. Okay. Yeah. Yeah. So the longer the carbon chain is, right, that's going to make it harder, right, in that terms. Mm-hmm. Mm-hmm. That's right, because the alcohol has that carbon chain, right? So then it'll be able to interact with the carbons interacting with each other as well. Okay. Okay. So now let's go ahead and get started. That took a little longer than I anticipated. Okay. Okay, so we're going to be talking about isomers. We've already talked about what isomers, the definition of an isomer is what. Same chemical formula, but different structure. Okay, so there are going to be different types of isomers. One of them is called constitutional isomers. So those are basically the isomers that we've been used to. It's connectivity, how they're connected to each other. Okay, so constitutional basically means how they're connected to each other. The other one is called stereoisomers. They're basically the same connections, so they have the same type of connections, but they're arranged differently spatially. Okay, so it's kind of like left-handed versus right-handed, right? Same structure, right? My thumb is still, I have a thumb connected to, okay, but spatially they're different, right? They don't fit right on top of each other. Okay, they're mirror images of each other. Okay, so that would be an example of a stereoisomer. Okay, so we have what we call conformational isomers, right? So conformational isomers, they can't be separated, right?
You're still on my board.
No. Sorry.
On our end.
I'm still on my board and you're in. Okay. Does that help?
Yeah.
Okay. So isomers altogether, we have constitutional isomers. So that's just what we're traditionally used to, right? So when I talk to you guys about I talked to you guys about sugar, like fructose versus glucose, right? Sucrose versus glucose, same chemical formula, but how they're connected is different. Okay, stereoisomers, they have the same connectivity, but they have different spatial arrangement. Then we have what we call conformational isomers. So these guys, they can't be separated in terms of they're spatially, they can't be separated, right? Where configurational isomers can be separated. Okay, and we'll go over those and I'll show you examples of that. Okay, so the conformational isomers that can't be separated, so these guys are going to be able to rotate around the c-axis, right? So with a single bond, so you're able to get that rotation, or you're going to end up with an amine inversion, meaning that it's on another side of the amine, so you don't have the attachments the same. So you have one over here, and then you have one over here on the isomer. Okay, so in the case of the amine group. So configuration isomers. So these guys are going to be your cis and your trans. So remember, cis meaning the same side, trans meaning across. And then you're also going to talk about isomers that contain asymmetry centers. And so we'll talk about all of these in this chapter. So let's start with the basics. Constitutional. So these are the ones that we're already used to. Okay, so here we have ethanol, diethylamine. Now they have the same chemical formula, right? But they're attached differently. Okay, we have pentane. Jesus Christ. Did you guys look outside? Oh my gosh. Okay. I hope my car is going to be okay. My little car is going to be blown away. Jeez. I know it's starting to get worse. I'm going to keep my, make sure, pay attention. We may get a, what is it? I was going to say hurricane. Not a hurricane, but I guess it would be we're too far from the water for a hurricane. Okay, it's been a rough day. I had too much time, too much good time on my vacation, you know, can't think straight. Okay, so back to this. So here we have pentane and isopentane, right? So in this case, again, the connections are different, okay? It's clear, okay? So here we have one chlorobutane and two chlorobutane, okay? So the location of the butane is at a different location, a different connection, okay? So those are, again, constitutional isomers, okay? Okay, so next, system trans. Can you guys hear me?
Yeah.
Okay, Abby lost us for a good few minutes. Okay, so cis basically meaning that they're on the same side. So here they're using basically a, you guys remember a dash wedge model, right? So in this case, can you guys do me a favor? Can you guys, you have your, yes, take your boxes out. Okay, so do me a favor. If you guys have your models with you, can you do a model of the very first one? This one. Go get it. So in the wedge dash model, the wedge basically means it's coming out with you, right? And then the dash means that it's in the back. Yep. Okay. So if the substituents are on the same side, it's okay. And if they're opposites, okay. I could tell. I can tell the people who play with Legos. What was that? Yeah. Yep. Nice, nice. So that would be cis. Yep. Okay. And then I'll make it trans. Does it matter? No, because you have two moieties that are across from each other. So no, it really wouldn't matter because it's, you got to remember your carbon's rotatable, right? So if they are to an extent, but trans just basically means that they're sitting on both the same side, right? I mean, trans, opposite sides, not the same side, opposite sides. So, okay. So yeah, if you flip one up, yeah, that's, yeah. So now you flip it over, it's the same, right? Only thing now one is coming out, one is coming in. So it doesn't matter. You see? Yeah. Okay, so when we start getting double bonds are going to restrict that rotation. Yes. Well, because they're letting you know that one of them is behind. Yeah. So you can tell one is front, one is behind, right? Where this is cis, both of them are front, right? You could have made this guy behind and then this guy front. Does that make sense? Yeah? Sort of. Okay, so as I was saying, the double bond, it prevents the rotation. So we're not able to rotate the way that we can in the case of the single bond. Don't take it apart, keep it. Okay, so we're going to use the two isomers that are on the screen. Make those with your kits. I mean your models. Well, it really works well with the long ones, yeah. Make the cis, then make the trans. Yeah, use the fact that you already have one of them already made for you pretty much. That's all right. She's like, I just like doing extra work, you know. I like to make it hard for myself. Is that right? Look at what is on the board. The chemical structure, how many carbons? There you go. That's cis. That's right. Ah, see, but you see, that's the point, right? So here, we also could have cis or trans, but you can't rotate the way we can with the single bond. So you notice that? Can you rotate the way you can with the single bond? No, you can't. So literally you have to unplug and plug, you know. So with the double bond, you're not able to rotate. Right? You lack the rotation. Okay. Where's your double bond? Make a double bond. You want to show them your double bond? Let's see your double bond. Have you put a double bond up there? No. Yeah, but put a real double bond because it doesn't mean this. It's quote signifies double bond, but it doesn't give you the limitations to a double bond. Everybody got that? Let's see. And you see how that double bond plays out. It prevents you from doing that rotation. You can't rotate. Right? You're limited, right? Okay, so that's exactly what's happening with the bonds, with the double bonds. Sorry, guys, on the other side. Like, can't keep remembering. I can't forget that I can't walk around the way I want to. So you can't rotate it. Okay, let me borrow yours again. Did you see your structure? Does it look like this? You have a double bond on one side, and you can't rotate, right? Okay. So
yeah.
Okay. So to get trans, we literally have to flux. That's right. They can't rotate. So triple bonds, and that you're going to end up with a linear, like triple bonds linear structure because of that, right? So that's why I draw it that way. I know it looks nasty, but they're limited because you can't twist them the way you want to, but you could change it, you could stagger them, right? That's what we could do. Remember, we could stagger them certain ways, right? And so because we can do that, that gives us some flexibility. So they have some, you know. Okay, so if we sit there and we think about it, so these are the boiling points, right? So if you take a look at the boiling points between these two molecules, they're going to be different, okay? Just by the, in this case, the cis or trans components of it, right? So, and if I remember correctly, so cis or trans, is that going to be a constitutional or is that going to be a spatial? Cis and trans, is that going to be constitutional or is that going to be spatial? Or is that going to be an isomer? I mean, I can't even think, a stereo isomer, or is it going to be a constitutional isomer? It's going to be a stereo, right? So, okay, so the cis or trans isomers, they're going to have different properties associated with it, right? So in this case, the boiling point hopefully, like I said, we have cars at the end of the day. And I parked right next to the damn trees now. I'm like, God, that was dumb. And I have a big old branch on my car. I'm gonna be pissed. Um, so here we have the boiling point of the cis isomer compared to the boiling point of the trans isomer. So the boiling point of the cis isomer is higher than that of the trans in this situation. Okay. So I'm trying to think of it. I can't think of it offhand, but you know, to me, I would assume that I thought it would be the other way around. I thought the boiling point of the cis would be lower than, yeah, I would assume they would take less energy to sit there and do that than it would take for the trans, but you know, because of steric hindrance, but apparently that's not the case. It may have something to do with the fact that you have that polarity that's going on here, that slight polarity that's going on in the situation. So. Yeah, that's what I would assume that it would be the cis because that higher energy that would be associated with it. Because these are both methyl groups here. This one is going in trans, but how they're going, I think it may have something to do with the polarity because we know that the polarity is going to change with the case of the double bond, right? So in this case, we're both moving towards the double bond. This one is moving towards the double bond in this way. This one's going towards the double bond that way. So then, you know, I don't know. I still don't. Logically, I can't figure it out. I'll have to think about it a little bit more. That's actually a good question. Very good question. Because I would assume that this would make, because if we think about the surface area, they're going to be about the same surface area. The only distinction is that we have the dipole moment moving in this direction on one side compared to the dipole moment. And maybe that's it, because the dipole moment is moving in this direction. That's right. So, but I'll have to research that one for you. Just can't tell you off the top of my head. Okay, so here we see the same thing in the case of this cis or trans, right? So they're both on the same side, right? This methyl group. So the cis molecule has a higher boiling point than the trans does, but that seems to be the general trend, right? Cis is more, but you may be right that more energy to sit there and disrupt the cis molecule than it is. So suggesting maybe a little more stability, which is odd because I would assume that the trans would be more stable. Okay, so some of the alkalines won't have a cis or trans isomer, right? So if obviously if they're going to be the same components, you're not going to have a cis or trans as a result of that. And okay. So again, here, same components, you're not going to have a cis or trans in this situation. Okay, so here, different conformations or conformers of a compound can't be separated, right? So we have two conformations, right? These two are different conformations. One of them is stable and one of them is unstable, right? Can you guys hear me?
Yeah.
Okay. I see that Ivy, our telephone pole guys, just got knocked down. Okay, can Abby, are you, did we lose you completely?
Yeah, I think she disconnected like 10 minutes ago.
Okay. So I'll say the recording for her. Hopefully we have a recording. The rate that things are going here. Okay, so if your compounds have different, they can be separated, right? So if we have different conformations that can also be separated. So in this case, we have a different conformation. So now we, instead of having the tail, we have the tail on the leg and the, okay. So in this case, yeah, I think we're having some troubles. So hopefully we stay intact for a while. Okay, the cis and trans isomers have different configurations that can exist, right? This is just another example. So here, cis or trans, right? So these guys are going to be cis, these guys are going to be trans. So again, the hydrogens, if we look at the hydrogens are going to be cis to each other. And here the hydrogens are trans to each other. And that's also the same thing that's happening with our substituents. Okay. So which one of these are cis? Which one is trans? Are you sure? This is actually a loaded question. Okay. So when we get into situations where we can't distinguish between what's cis and trans, because you no longer have one of them that is going to be a duplicate of the hydrogen, right? So we have three different priority groups, three different substituents. We have the bromine, we have the chlorine, and we have the methane, right? So this brings us to this other system, right? So it's going to be based upon priority. So we have what we call the EZ system, Z standing for the Zeus summon, which means together. So then that means that your lowest priorities are put together, your highest priorities are put together on the same side. Okay. The E isomer would be lower priorities on opposite sides, higher priorities on opposite sides. Okay. So, and this is the antigen. So in that case, so in this situation, these guys have, although they're halo, right? They are considered to be slightly more priority than this side chain. Okay. Even though these are alkanes and these guys are halo alkalides, they're technically at the bottom of the. So we put them in terms of functional groups. These guys would fall just slightly above these guys. Okay. And then of course above hydrogen. Okay, so this would this guy be cis? I mean, would this be Z or would this be E? The first one. Z. So both with the higher priority on the same side. So this guy would be a Z. Okay. And then this guy. Does that make sense? Okay, good. Yeah. It's whatever functional group it is. So there's a priority list. But the problem is that at that bottom of the priority list, it gets a little hazy, right? So alkaline, so we have, alkanes, alkenes, alkynes. Those guys are all they're considered to be the equivalent when they're functional groups or they're substituents, the side chains when they're the side chains, right? So they're the same level. Alkaline halides, right, which is what these guys are. These guys are technically, they should be lower in priority, but when you take in consideration the cis and trans, they are higher in priority than the alkane. So this guy is lower in priority. Okay. Unfortunately, there are inconsistencies in OChem that they haven't quite figured out how to revamp them, and that's one of those inconsistencies, right? And so you'll see that happening quite a bit, unfortunately. Okay, so this is just showing you that priority, same side. So this guy's our Z structure, opposites E structure. Okay. Okay, so let's see. Let's do. So let's say we have this guy. Okay. Okay, which one is going to have the highest priority? The alcohol would have higher priority. Okay, so we'll say HP. Okay, so which one of these three are going to have higher priority? So this one? This one here? Oh, this one. Okay, so remember, this is a alkane. This is an alkaline halide. I think I misspelled that. And this is also an acyl halide. So, which one is going to have the strongest electronegativity in this case? Between these two alkaline halides, the bottom. Okay, so then this is going to also have a higher priority. So HP, so we have high priority on both sides. Is that going to be Z, or is that going to be trans? I mean E. Sorry, Z. Okay, so this guy would have a Z, would be a Z isomer. Okay. Yes, sort of. Yes, but then you have to think about priority when so this is only when you can distinguish between the two, right? So like if you have a hydrogen, and then, okay, so Z is based upon priority, right? So. Okay. So there. Okay, so you guys see that? Okay. Let's do this. What about, let's see. H2. Okay. Oh. So in terms of priority, I should also tell you this. So we have, when we talk about the alkalines, they kind of fall sort of together, right? They're grouped together when you're comparing to other things. When you look at them independently, alkanes are the lowest. Alkyne are the second lowest. So alkanes are all single bonds, right? Alkyne is a triple bond, And then alkene is a double bond. Double bond has priority over the triple bond. The triple bond has priority over the single bond. Okay. Okay. So if we have something like this, okay. So Z or E. Okay. So this would be an E isomer because this has priority over the triple bond, which also has priority over the single bond. This has priority over all three. Okay. Are you guys with me? Yeah. NDC, you guys with me?
Yeah.
Yeah.
Okay. Okay. So you guys want to take a small pee break and then get back? Okay. So let's take a, we'll say I'll see you guys back here at 3:15. For those anybody who wants to go out and bear the crazy weather out there. Okay, so here's another example. You guys can see. So we have double bond versus triple bond, single bond. So this guy would have been Z. This guy would be E. EZ. Okay. So again, double bond. Yep. Okay. Double bond would have priority. And that's deuterium. That's what the D stands for. Deuterium. Deuterium is it is a, I'm trying to think of it, an isotope of hydrogen. So, and this is just another example. So in the case of deuterium, yeah, bless you. Bless you. Okay. Okay, so we have chiral versus achiral. Okay. So, and these guys are going to be chiral, right? Our ears chiral to each other. I don't know what the hell that is. It looks like a seat.
It's a
Car seat?
car.
Car seat. Okay, car seat. Or the front, like the front seat of the car. Okay. Yes. Okay. Ah, okay. I guess I see it. Sort of. Yeah, I see the steering wheel now. Okay. Yes. Okay. So these guys, the chiral structure, they're not going to be imposable, right? So they can't be imposed upon each other, superposed on each other. So like a hand, you know, we put them right on top of each other. Thumbs here. Okay. Where in the case of a chiral structure is superimposable. The fork, the glass. Okay. Okay. So here, so a chiral molecules are they're going to have a asymmetric center. Okay. So it's going to lack symmetry, asymmetric. You guys remember that from, I don't know, 2A, we talked about it. We talked about it in, yeah, in 1A. Yeah, I can't remember if we did or not. No. Okay. I know we talked about polarity. And when we talked about polarity, we touched on it. Yes, we did. Yeah. Yeah, we did. Okay. So if you guys remember, so this guy would be considered asymmetric, right? Here's your center carbon. We have a methyl group here. We have a bromine group here. All right. So it lacks symmetry. In this case, we're literally talking direct symmetry, right? Okay. So this guy would be definitely asymmetrical without a doubt. Okay. Because we have 4 different things attached. Okay. So here we have, these are all examples of asymmetry. 1, 2, 3. On the 4th carbon, then we have 1, 2, 3, 4 carbons are here. So there's 3 carbons here, 4 carbons here. And then we have the ethanol that's hanging off that 4th carbon as well too. You guys can clearly see this one too, right? So 2 carbons over here, 1 carbon over here, and your bromine. And then this point right here, clearly asymmetric. Yes, no, maybe. Okay. Okay, so now I'm going to introduce you to enantiomers. Okay. So these guys are 2 stereoisomers of the same molecule. So this is 2-bromo butanol. I'm sorry, butane, not butanol, butane. 2-bromo butane. So if you take a look at it, these guys are mirror images of each other. Right? So if we put them on top of each other, they're going to be different. Right? Okay. So these guys are called enantiomers. Okay. Was that a lot of definitions? Yes. Flashcards, bless you. So now enantiomers, they're going to be different compounds. So they can be separated from each other. They have enantiomers. They're going to have the same physical and slightly some of the chemical properties. Okay. So this is just a generic form, just showing you what an enantiomer looks like. So these guys are not superimposable on each other, so you can't just put them on top of each other because they're mirror images. Okay. So this is just showing you the chiral molecule. And then you guys can see that they're not, superimposable on each other, the mirror image. Where an achiral molecule, those guys can be superimposed on each other. Let's see. Okay, so if we flip this guy, right? All it is flipping this guy and it'll be exactly the same thing, right? Meaning that if I just turn on that axis, right? Just because remember, the C is rotatable. So all we're doing is rotating along the C axis. Or even if I rotate on the C axis, these guys aren't going to be the same. Does that make sense? Can you guys see that? Okay. So that's why it's important to pay attention whether or not you have a symmetrical or asymmetrical center, right? Because then that lets us know whether or not we're going to be able to have a chiral molecule or I should say chiral molecule or a chiral molecule. Okay. Okay. Are you guys good? Okay. So these guys are called your stereocenters. Okay. This guy is an asymmetrical center, where these guys aren't. Okay. So asymmetric, okay, atom attached to 4 different groups. Stereocenters, atom which is interchangeable of 2 groups producing a stereoisomer. So okay. So this is how we would draw the enantiomers. So you guys can kind of see with the dashed and wedge. Right? Enantiomer is achiral. Yeah, achiral. Yes. Not, yeah, not. You know what I'm saying? And that's what I hate the damn word. It's, let me type it out. Yes, that's right. So enantiomers are okay, and not, yeah, and not a chiral. You see the distinction? Yeah, I know it's subtle. Okay, so this is called a Fischer projection. Yes. No, this is an enantiomer right here. This is an example of an enantiomer, right? So the fact that you have the mirror image of each other, if it's a mirror image of each other, right? You can't transpose it on top of it, superimpose it on top of each other, or transpose it on top of each other. It doesn't look exactly the same. So then those are going to be enantiomers. Does that make sense? No, it's achiral. Pretty sure. Let me go back. No, you're right. You're chiral. My bad. Achiral is when they're superimposable on each other. I got it mixed up. My bad. So enantiomers are chiral molecules. Thank you. There you go. Okay. So these guys are going to be mirror images of each other. And then if we take a look at this, this is our Fischer projections. This is worrying me a little bit. I don't know. Fischer projections. This wind is crazy and the dust is crazy. Are you guys, who's driving home from here? Like, well, yeah. After this, be careful. Be real careful because it's crazy out there. Yeah. Oh, yeah. I'm right there with you. Okay. So Fischer projections is just, you're going to use the cross, right? And it just shows you the asymmetric center. That's going to be our carbon in the center. That's going to be represented by that. We have 4 different attachments. Okay. So, and then you can show easily, right? So these guys can easily show, you have your methane up top, your ethyl group on the bottom, your bromine, in this case, to the left, and your hydrogen to the right, and then that will be just the opposite. Okay, so again, Fischer projection, just using that cross, right? Because we know 4 attachments, 4 different attachments, and we're the ones that are not imposable on each other, that are going to be in that plane right there, the center plane. Okay. Okay. So we look at the assignments. This guy has priority 1. This guy has a second priority because it's longer than the methane. So that's 2, 3, and hydrogen has the 4th priority. So in this case, this guy is 1, 2, 3, 4. Okay. So if we're going counterclockwise, then that's going to be S. If we're going clockwise, that's going to be R. I also like looking at it as, okay, so going towards the right, R. S also stands for sinister, left. All right. So counterclockwise to the left, S. Okay. So clockwise to the right, counterclockwise, clockwise to the right, clockwise R, counterclockwise S. Okay. So that's how we would distinguish. You know that it's on the second carbon. So this guy is going to be called S2 bromo butane, where this guy will be called R2 bromo butane. Okay, so sometimes what you'll get is a mixture of both, right? So like for instance, one of the chemicals that we have in there is 2-bromo butane. It doesn't distinguish between the S or the R, right? So when they're made, there was no distinction between the two. It can go either way, right? And because they have their chemical properties are going to be the same, and their physical properties are going to be the same, it's going to be hard to distinguish between those two, right? Separate them. You have to polarize it to get it to distinguish, which takes a lot more effort. Okay, so now remember when you asked me about the wedge and dash, does it make a difference? So in this case, it's going to make a difference because we have 4 different attachments, right? Okay, so in this case, the lowest priority group is not the hash, right? So right now, this is the hash, so that's the 4th, right? So 1, 2, 3, 4. In this case, 1, 2, 3, 4. So is this guy cis? I mean, is this going to be an S or an R structure? Okay. And this guy So this guy is also an R, but we wouldn't put the H on the lowest priority, right? So that guy gets 4, 3, 2, 1. So 1, 2, 3, 4. Yeah, so in this case, well, it's so yeah, so this guy is rotated on, it'll be rotated on that C-axis, right? In this case, because you're keeping these guys the same and you're switching these two, right? That's the solid one. The dash, that's the dash. The hatch wedge is the solid one. So this is the molecule has a R. Okay, so then therefore this guy would be the S version. Which is weird, right? Is that right? Switch. Exchange. Yeah, exchange the two. This guy? Yeah, it's still an R. This is an R and this is an R. They're both the same. Yeah. Yeah. So the molecule is the molecule that has the S configuration before the group were exchanged. Let me think about this. Hold on. The molecule has the R configuration. Therefore, the molecule had the S configuration before the groups were changed. That's 1, 2, 3. This is going clockwise. So 1, 2, 3, 4. So that is going clockwise. So it's still an R. I don't know what they're trying to get at here. 1, 2, 3. That's what I believe it's trying to say, but they said it was an S before it was switched to an R. So, but the rule is that you're not supposed to have your lowest priority should not be the one that's coming out of. Right? And so you need to orient it so that it should be the one, it should be higher than the lowest priority. So your lowest priority should be goes towards the back in this situation. So in this case, was that? Yes. And then your front and your back go are dictated by whoever's lowest. Lowest goes towards the back. I mean, so yeah, lowest goes towards the back because the dash. Yeah, yes. Put yes. The lowest person is in the back. Right? Yeah, I need to take a look at what they're. Okay. So if we do it with the R, if we do it with the, I'm sorry, with the Fischer, right? So that's 1, that's 2, that's 3, that's 4. So this guy is clockwise. And this guy is counterclockwise. So in other words, that fourth position, this guy here, it's bypassed in this structure, right? So you're going 1, 2, and then you go to the third one, right? Because it's the third priority. Yeah. Yep. Okay. So if the lowest priority group is on the vertical bond, then R counterclockwise is S. Same thing, right? Okay, so if the lowest priority group is on the horizontal bond, okay, so then that's 1, 2, okay. then in this case, counterclockwise is R, clockwise is S. So that's 1, 2, 3. And then in this case, 1, 2, 3. Now, I'll have to remember that myself because I don't remember all of this. Okay. Okay. Your class is over at 4? Okay, making sure. Okay, so when we talk about plane polarized light, okay, so here, if we take a look at our light source, so normal light is being scattered in all directions. Polarized light is going in a single direction. So if we have a polarizer, we're going to get a single plane that's associated. So you guys remember when you did, remember when we talked about the spectrum? And then we were looking at discrete lines, right? So if we look at the diffractor, the slide that we used, that gave us the light being polarized, right? So if you kind of remember initially, if you take a look at it, it's like white light is kind of spread all over the place and everything like that. But we were able to sit there and individualize the individual lights when we had it from that single source, like hydrogen or something like that. We got those discrete lines. It wasn't doing a little haze thing going on between the two. Okay. So in that case, we are polarizing the light in that sense is being polarized because you have that single electron that's doing it in that circumstance. Here, normal light going all directions. We're using a polarizer. The polarizer is orienting the light. So it's going in a single direction that is being propagated. Okay. So that's why you're getting, in this case, normal light spread all over the place. Polarizer, the little light rays going in all the same directions in a single direction. Okay. But it's going to be oscillating, right? So then that's why you get a line of light, no line of light, a line of light, no line of light. Why is it oscillating? Anybody remember? No, it's for, you can use an electron as an example, but it's not only the jumping component of it. Think about what is the definition of a light wave or a light ray. Oh, did you say wavelength? So why do you think it's oscillating? Because it's a wave of light, right? So light is actually a wave. It's a wave that's being radiated, right? So the oscillation part of it, that getting the polarized component and then the non-polarized component. So when they're able to cancel each other out, you're getting a non-polarized. Polarized is when they're being constructive, they're making a single. Non-polarized canceling each other out. So constructive, cancel, right? So because of that, that's the reason why you're getting the oscillation. And that's why you're getting the oscillation between them of those polarized waves. Where here, if you take a look at this here represents light going in all those directions, right? That's what this is representing. Here's representing that polarized plane of light. Okay. So, and here, and a chiral compound doesn't rotate the plane of polarized light. of plane polarized light. Okay, so if we take a look, here's our polarizer. This is what it looks like initially, and this is when we have a tube that is containing a chiral compound. I know it's killing me too. A chiral compound. Okay. So when we have a chiral compound, it actually is going to rotate that plane, right? So because it rotates that plane, instead of having them straight up and down, now you have that angle because it's rotating. So you get your little rotation going on, right? Okay, so if it rotates the plane clockwise, it's considered to be plus. If it rotates the plane counterclockwise, it's going to be considered minus. Okay, so we talked about the S and the R, right? So we also talk about that polarization. So that polarization is rotating in the plus direction, clockwise. It's going to be a plus, so we're going to add a plus. If it's rotating counterclockwise, then it's going to be a minus. Okay. So we have S plus lactic acid. Okay. So this is S minus sodium lactate. Okay. So some are enantiomers are plus and some are minuses. Okay. Some S's are going to be plus and others are going to be minuses. Okay. So they don't mean the same thing. So that plus and minus refers to the polarization. Okay. Excuse me. Okay. So this angle, right, can actually be calculated by this equation. And so I should say this here is going to be the angle of polarization. It's going to represent, I'm sorry, this is going to represent the temperature. My bad, temperature. And this alpha is just going to be represent that technically the distance from that point to that point. So the distance that you've altered your angle, right? It's going to be the distance, I believe. Yeah. Let me confirm that. I'll confirm it again, rusty. So I'll confirm that for you. And then let's see. Let me do a confirmation on this entire thing.
That was loud.
Okay. You can fall through the stairwell. Yeah. He got up and walked. Okay. So I'll do a confirmation on the equation. I have to get refamiliarized with it. But we do have a polarimeter that we're going to be using. So yes, did the second one come in yet? We only got one. We got two. Okay. So yeah. So I'm going to stop here.